Let me take the privilege of introducing Dr. Kavira Nishikant to all the participants. Dr. Nishikant is presently an associate professor in Gayatri Vidya Parishad College of Engineering, Vishakhapatnam, in the Department of Electrical and Electronics Engineering. He is an entrepreneur and has a technology firm working on medical devices where his former students are employed and are working on healthcare products for elderly people. He has to his credit over 60 research articles. His interests lie in medical robotics, time delay systems, and intelligent systems. He is a senior member and life member of several research organizations like IEI, ERTA, IEEE, ISRD, IUCEE. He is also a reviewer of popular journals like International Journal of Fuzzy Logic and Intelligent Systems of Korea, IEEE, Elsevier, Teleron Francis. He has organized many workshops, FDPs, conferences, and is an active researcher and is presently guiding one PhD student working with the Border Security Force. He has been the recipient of ERDA Excellent Award for Teaching in 2024 and has other awards to his credit. So, with these words, I welcome you once again, Dr. Shrikant, and as a as by the scheduled time, sir, now you are requested to start your session. Over to you, sir.
Thank you very much, madam. I have over 90 slides. Hopefully, I will complete as per our schedule, because this control systems applied or using AI is a very vast subject, and I'm just trying to bring a snapshot of uh, over years of my work and what I've learned with different organizations. So I hope my slides are moving. Did my slide move, madam? Okay. So first I have to thank some of my former professors, like my former advisor, Dr. Robert McLaren. He was a professor emeritus in University of Missouri, Columbia, USA, 25 years back, and Professor Bernard, who was author of 2 control systems textbook. He happens to be a friend of Kalman, whose work on Kalman filters we normally read. So these are 2 distinguished people. I had the opportunity to interact and learn some bits of control systems from them. I'm very much thankful to them for training me on some aspects of control. So this journey is long dated, so I'll move on. So when it comes to control, okay, most decisions these days are about linked with human beings. And in the recent course I was doing, or the interactions with Professor Srinivas Chakravarti from IIT Madras through the course on demystifying the brain, there was one statement which it says, when it comes to brain science, if we separate principles from details, complexity does not disappear but ceases to be intimidating. It is like the level of AI that is entering will be more intimidating in the near future. So that is one analysis that is resulting in more thought process for the control engineers. Now, my talk as such today will be for on the topics of AI and electrical engineering, and basically AI and control engineering, how we are doing automation, and then how we are helping like some parts like AI ML for helping PID tuning, what are the case studies, what is real-time system regulation, how we do to adaptive control using AI ML. So uh, so this is a typical classical control problem, which many people are familiar with. If you look in the left corner, the topmost where you have a control block, you would have a plant, you would have a controller, you would have a feedback element. Now, with AI, what happens? This particular controller will be a AI tuned PID or maybe a sump controller. And in the feedback loop, instead of having a regular feedback controller, you would have a AI based feedback controller. So that is how the implement would take place. So if that is the case, and how we are trying to tune the plant, and how we are want to obtain a particular desired response, is what is of interest for us. So that is from a control engineering perspective. Now, where does this journey start with? As such, if you remember, the journey of controlling anything or making something or making things to start with hand tools. Then we had power tools, and then we had fixed automation as one aspect, and then we were having robotics. And then today we are in the era of intelligent systems. So this era of intelligent systems is where we are mostly relying on AI, which is helping us with automation and time saving procedures. So if you take a typical example of a loop that I'm talking about, like for instance, a mechanism where we are trying to take a decision, and if you try to give a control block diagram, you can just see how many things are uh, going to decide. Like for instance, when you have to apply a brake to control your vehicle. So it is not the basic observance that of that of a vehicle that will decide what you have to do. It might be like what are the circumstances, what has come, like what is coming as an interference, or maybe what is the outside information, what is there inside, and uh, what are some of the orientation. I mean, some decisions require some analysis synthesis, or the heritage will help us decide. So the process of decision making as such is complicated when it comes to humans itself, and this involves a lot of time consuming aspects, which when we impart AI would be more of a complex dynamic system. So for instance, if you take this image, here you can see the monkey learn, right? So what is that monkey doing? Is using AI? I mean, we are seeing that this monkey is not as such using AI, but it is just typing the typewriter. Now, if we have to train the monkey to use a keyboard, how is it that we do? Do we use AI, or do we teach it with some kind of technology tool? How did human learn typing, and how do you teach that to a monkey? So these are like things when it comes to some aspects of AI. Now, let us say we take the aspect of data mapping with AI. Okay, for instance, here you can see a small joke where a doctor asks a old person how his memory is holding up, and he says he has to put a tag of wife on his wife's forehead in order to understand how good it is. I mean, that shows the problems. So these kind of problems are what have to be controlled or to be solved with our AI. Now, this is one aspect of my research, which for because of which we are doing some projects, and then how it is related to electrical engineering. Now, if I take this example of a conjoined twins, okay, so two brains, and we have one body. So which brain is sending the signal, and which brain's signal has the body has to obey, or which is controlling the body? What brain is controlling the body? Now, this is the control, the complex control system. Okay, so if we are taking the complexity, the analysis, now this is a difficult problem that have to be solved. Okay, so if we are integrating AI, maybe we can solve some problems for situations like this. Now, how do we coordinate this? So it would be like you would have to understand most things are being interfaced by taking something like a brain computer interface, and then human computer interaction, man machine interaction. So typically how we take the BCI interfaces, or like we take the signal acquisition, and then we process it, and then we command. This is like one type of control that we are these days people are interested in. So if we the past 4 days I was listening to many speakers because I didn't want stuff to overlap. So we have seen topics on load forecasting, and then generation forecasting that were discussed by speakers from different parts. And then we have learned what is AI, what is ML, what is neural net, what is deep learning. Okay. but I've seen not many have gone into depth of what is called as an expert system, which is the requirement for control. These days, more of expert system analysis is what is the need of the hour, which is prompting us to learn this AI related control engineering. And then if you see, there are some extensions to this, like the computational intelligence aspect and fuzzy logic, which are another a wing of the same research that people do. Now, what we are enabling, what technologies get enabled with AI is like we have to have vast amounts of data. So this is like the big data era where you store information in cloud and then you access it for taking a timely decision. And that data mining has to happen. So this has given us to evolve into data science engineering. So that is another dimension of the control engineering, because a control decision has to happen only with the proper access to data, which is mined or accessed or extracted at the correct time to analyze. So if we are seeing at the entire arena of intelligent system, which we are doing, so basically we are having overlapping circles of fuzzy logic, computational intelligence, machine learning, AI, deep learning, expert systems, data mining, and all. So people work on different aspects, and then we try to understand. Okay, so as such, the field of AI is about planning, learning, problem solving, and it is just expanding. So we have heard speakers in the past 4 days talk about something like supervised, unsupervised, reinforcement, semi-supervised. Okay, so there are recent research papers where people are talking about federated learning. It is like training AI without sharing raw data. So more of another dimensional aspect of the AI component. So typically what we see is we will have a objective which is to be achieved with the different training algorithms, and we try to see what is the time scale on which we are achieving that, and then how much time each is responding, or what is the optimal way to reach the particular goal. It has been one aspect of learning. So as such, AI in electrical engineering, like basic analysis we have seen, like in the aspect of load forecasting, or maybe generator forecasting, as we have seen in the earlier days, last few days. So there are like the product-based engineering, because AI being used for some innovative product. So when we talk about innovative projects, some smart refrigerator, air conditioners, microwave oven, rice cookers. So how we make them smart with the AI part is something that is evolving. So they say AI brings the heavens to the world, based on one of the statements of one control expert called Michio Sugino on control. And then some people have said fuzzy is like William Kahn says, fuzzy is the cocaine of machine intelligence. Now that might be replaced by somebody saying AI is like the cocaine of machine intelligence, which will lead it. Okay, so with AI, what we do is I am the best. We try to update the best, or we keep updating to become the best. Okay, so it is like one of the eminent persons, Booth says every system is its own best analog. So when we say analog, what we try to build, how we try to make it the best. So that is what is the system level modeling. Whenever we are having a system now, when we talk about a control engineering, before we talk about a controller, or before we talk into the control engineering aspect, or the feedback, we have to also understand the system level modeling and how AI embeds into the principle of I'm the best and I update to remain the best, or make the system the best. Okay, so we have to understand the adaptive nature of AI and how we can use it for optimization, for intelligent automation, or for controlled or regulated automation. Okay, so this is like if you're taking a circuit design. Okay, so how best we can understand the RLC circuit and how we can make it better. Okay, so that is one way to look at it. So what is important when we are doing control? Okay, so when we are doing control, we have to understand AI used for abstraction and AI used for accuracy. So abstraction is like understanding the system, and accuracy is a precise. I mean, we are trying to get the exact result. Okay, so traditionally, if we are talking about a classical control mechanisms, these are rule-based symbolic AI, which were defining what is the problem, what is in reality what is happening, and we are trying to interpret it with the abstraction. So that was what the traditional AI or AI abstraction was doing. With the modern AI, we are improvising and we are using something like deep learning, which will improve the accuracy, and we are modeling complex systems using vast data, okay, which is like maybe a data in cloud or maybe somewhere it is stored and we are trying to access it. And then based on the earlier philosophy that we have understood, we are trying to make our own best analog. So that is what we are doing with this particular AI in control. Okay, so when it comes to AI in control, if you go a little bit deeper, it is like they always say that the devil is in the details. So AI excels in capturing nonlinearities, hidden dynamics that are difficult to model analytically. So it is like when we are analyzing a complex dynamic system, and if we are trying to understand the system as such, so AI will help us understand the very intricate aspect. Like in the classical control, what we were doing with the frequency domain analysis in place of time domain analysis. So whatever we could not achieve with the time domain analysis, we were doing it with the frequency domain analysis. Now, whatever we cannot do with the frequency domain analysis, we can do it with the AI based analysis. Okay, so that is like the extension. So when we are talking like something like a fractional order system analysis, it can approximate such behavior with learning properly based on the learning of AI, rather than the classical methods which were used for calculating a fractional order control system. Okay, so traditionally we were like, about 25 years back, maybe I've used what is called as the system identification method using neural network models, and we were trying to train neural networks for control of a inverted pendulum. So inverted pendulum as such is a classical control problem, which is like a test bed for using any control or developing any control strategy. Now, identifying the system, understanding the system, there were tools with different softwares like the Box-Jenkins model, which were used for understanding and interpreting and developing a system model and then trying to control. So that was like the classical control where you integrated the neural network aspect. So not today, but 25 years back itself. Now with this, what are we trying to achieve? What we try to achieve is automation with AI. Okay, so it is like whatever human like cognitive abilities are there, like the pattern recognition. One of the example madam was showing the other day in the earlier lecture. Or if we're trying to have a AI driven automation to mimic human intelligence, and how we are doing. Okay, so the self-driving car. So the one of the important aspect of self-driving cars navigation is the control of the vehicle. So how well we are controlling the vehicle is a very important step in order that we'll be able to do some justice. Okay, so as such, if we try to define control engineering with AI, achieve accuracy and precision is one aspect with AI. So what we could not do with the classical control mechanism, we can achieve with the accuracy and precision can be done with the AI. And then 100% automation. Okay, so normally what happens, the ratio of automation would be defined based on how much manpower we require and how much machinery we are using. But complete automation, like the dark factories that are there in China, so maybe we can go with the dark factory concept if we are able to 100% automate with AI. That requires something like a safety and security issue. Okay, so because as such, when you're talking about a control process, this control process as such may be safe, but it might not be secure. It might be secure but not safe, safe and secure but not be precise, or safe, secure and precise but not automated. So these are all like the dimensionality of a control problem. When you're talking about a control, what we try to control will have different dimensions, and all these dimensions have to be analyzed. For instance, if we're talking about a circuit breaker, if we are talking about residual circuit, current circuit breaker, and how when it should operate, and what will happen if somebody has bypassed it. So it is like the safety aspect and all, and how we are actually trying to understand this. So these are like the objectives of control engineering and how we are trying to incorporate AI into the control engineering. Okay, so one of the important things when it comes to automation with machine learning for proper control will be how we can define a control law, how these control laws are constrained with machine learning. So when I say that, what does that mean? So traditionally, if we are talking about a control law, a control law might be a linear law or a non-linear law, and then we try to define it based on a pole location, or maybe define the control loop. We see the output characteristic, we see the time domain specification, or maybe a Bode plot, and try to understand it. Now, whatever we were trying to do, the same thing, the control law are constant with machine learning. It is like you define the envelope, the boundaries or limits will be established by the AI, and then we train the algorithms, and then we do it. Okay, so as such, we are talking about an industrial automation pyramid, which is like very important. And the basic level of the automation pyramid would have sensors and actuators, and how the sensors are integrated with the actuators, and how the actuators are controlled is one key aspect for the hierarchy of an industrial automation pyramid. So our simple actuation tasks have to be precise, accurate, safe, secure. Okay, so there are n dimensions that have to come into picture, which will make the industrial automation pyramid correct, and then we'll have a product at the user end. Okay, so as the topic is more of controlling, I thought I just will give an overview of what is happening, and then come into and narrow it down to some particular examples or case studies. Okay, normally, uh, uh, if you try to do a PID control, okay, as such for a plant or process that is defined, one way that we can achieve that is by using an op amp. Okay, so operational amplifier are normally used for doing a control aspect, like whatever PID control is there. The physical realization of the PID control can be achieved with the help of a device like operational amplifier. Okay, so when we talk about a device which is being used for as a controller, and we are trying to develop or control a complex dynamic system or any system, the device limits and how we can control the device parameters are some key aspects. Okay, so like how we are developing the circuit, and then what are the conditions under which that particular circuit is operating, or how the voltages are changing, and how we are defining a particular gain value based on the resistance, like RF by R would be something like a proportional gain. Now, if I'm defining the physical realization of a circuit with a op amp, and if I'm trying to achieve that value of RF by R correctly, there I might have to use a pen and paper and calculate it. But that can be done with your AI. So that is the advantage part. Okay. So when your the number of devices increases, it is like they say most controllers can be replaced by an operational amplifier based control mechanism. It is like you can build your control circuit using an op amp. Now, if you are using n number of op amps, and then if you are trying to define the ratios of RA, RB, RC, or RF, which are used as a controller in a particular circuit, how do I define these values is something that is very much important. And this is where the learning all the algorithms that we have used earlier can be imparted. So typically, where again, the important why it might be important to be accurate, because these it could be used for a electrocardiograph amplification value that is being measured, or maybe something else. Okay, so different kinds of signals for different instrumentation amplifiers for different analysis based on the requirement. So application specific, the control circuits vary very much, and then the requirements on how we are taking the values would as such be very difficult, and as such have to be very accurate, because if you are trying to do some measurements, they have to be accurate. Okay, and then if I try to integrate it with some other transducer, normally it is like a controller, and then we have a sensor which is like a piezoelectric transducer, which is used to measure force, pressure, or acceleration, and then we are generating an electric charge, and then we are trying to understand. Okay, so if we define this op amp circuit for a piezoelectric transducer, and then if you try to use this, okay, for some kind of a block diagram where I'm using a PID controller, where I have the sensors and the output process, how we achieve is what we can see. Okay, now this again might appear very simple, but the signal conditioning and how, as I mentioned earlier, how we are fine tuning the value using AI would be a difficult task. Okay. So this is one example, like a classical method of PID controller and the physical realization using analog, I mean analog sensors, and then we try to evaluate. Okay. So how we adjust the KPKI, KD values, and then if we are using different mechanisms of control, how we are using a relay-based control or a big bang control or different mechanisms, how we are achieving the values or how we are tuning the PID is something that has been a trouble for many years, because the PID tuning will be done maybe in a simulator or maybe some kind of analysis on paper and pen and paper, and then they try to evaluate and then see how the typical response is there and how the energy is varying over time. So if you are trying to take the example of an RLC circuit which is oscillating, for instance, okay, so how we are fine tuning it and how we are fine tuning the gain values and how we are applying that voltage. Okay, so typically it is like the frequency plays a very important role here, and then how, if I'm taking a capacitor voltage cycle, how it is changing is one important thing, and then with the variation in frequency for the same input, what is happening with the discharge cycles. These are things that are applied if you are taking something like a battery management system in an electric vehicle, and how the input and the output of each of these waveforms have to interpret it is something that is very important. Now, as such, when we are talking about PID controller and then op-amp based PID controller, we are talking maybe about using the combination of op-amp with the different resistors and capacitors and how we define the control. So as such, when we are building this, so what comes into picture is like maybe a analog PID circuit, the plant, the sensors, the analog to digital converters, whatever is the microprocessor or the controller that is used in the DAC boards or any digital to analog conversions. Okay, so the challenge lies in how AI can be used for tuning the analog PID. Okay, so excuse me. So we take the plant's response and then how we digitally adjust the analog components is what we can see here. Okay. So as such, the AI algorithm, whatever the n number of algorithms that were discussed in the previous few days. Okay. So they can be used for constituting or narrowing down to a good tuning. This could be like we can minimize the overshoot, settling time, steady state error, combination, or maybe the integral error. Excuse me, and then run the plant with various PID settings, okay, and see how we are collecting the data, and then we can use that data for training the plant, okay, training the controller as such, okay. So, excuse me, just 1 second. So, as such, the AI techniques, if we are talking about, so something like a AI agent interacts with the plant, and then we set up a set of rules, and then based on the rules, the error is calculated, and then we optimize the PID. So this is like a reward-based analysis, like the reinforcement learning, and then we can add different aspects of intelligence, like the genetic algorithms or naturally inspired algorithms, and then maybe use a combination of fuzzy particle swarm. There are a lot of research papers these days which are using different combinations of neural networks which are using different aspects of PSO, because PSO, these are like naturally inspired algorithms which are basically optimized. And now whatever we do, this algorithm, we use it for tuning the controller. Basically, we are making the AI more smart. Okay, so that is what is the aspect of analysis. So when it comes to the tuning process as such, we take an initial explanation. It is like the data set that is available. So maybe some data set you take, and then we acquire the data. The microcontroller reads the sensor data, compares it. Like we have seen yesterday, there were some examples which were applied, which can be used as a reference. So basically, we take the we ensure that the AI takes the decision, and then any adjustments are there, that is done, and then the iteration process continues, and the plant operates as per the desired response. Okay, so model-based AI tuning. As such, what we do here is we try to develop a plant model, we simulate and tune, and then we translate to analog component, and then we have the hardware implementation. So as such, all this can be done with different tools. Okay, so how we develop the plant model, maybe you use some kind of identification technique, and then we do it, because in most complex control analysis, you don't have a plant model, and then you might have to use a system identification where you study like the input output patterns, and then based on which you develop the plant, and then we try to simulate it using a simulation tool, and then maybe we translate to analog components. There is some crosstalk. Excuse me. Organizers, can you please mute other speakers, please?
Oh,
Madam, can you mute other speakers? Okay, thank you. So whatever I was talking, basically, if we are trying to bring it down to a block diagram, as such, we would have something like a manipulator or a robot arm or any automated device or machine that is working, and then we would have a process, we would have a machine learning, we will have optimization, and then we'll have the control process. So typically, this is what we do with the control engineering. Okay, one important aspect these days, at least in because control is an important parameter in industries. So we apply it to programmable logic controllers. So these are like one aspect of monitoring a machine. Okay, so after which we can apply something like a deep learning and then take data-driven decisions. Like if you are manufacturing or you want to change the thickness of the sheets that are being manufactured, or let us say some kind of a sheet manufacturing industry is there, and you're trying to automate the control process there, and the thickness have to be varied by a AI program. Let us say for every 100 sheets, the thickness have to be varied. And then if you are trying to automate it, maybe there you have to apply like something like a programmable logic controller, which is like one aspect of learning. Okay, so now traditionally we have machine learning and deep learning as such by CNN. These people might have seen in the past few days. So just quickly, if you are looking at these particular aspects, as such, we have learned about machine learning, and deep learning as such would have something like self-learning, and then we tune how we tune actually will differ. Okay, the self-learning aspect is what makes the CNNs more powerful, okay, which are applied in a control process. Okay, now how we can use the big data, and if you're trying to apply something like a PLC for a process control, is one aspect of research that is prominent these days. So that is the reason I thought I would bring up some slides on that. And then people are doing something like data learning for PLCs, and how we can use PLC to be more powerful, because classical relay-based control as such might not be efficient in all cases, and maybe a PLC might be a effective alternative to deal with a machine that has to be controlled, and we can optimize it by using something like a machine data. So smart manufacturing, robot grasping, predictive analysis, smart traffic case systems, these are some aspects of deep learning for the PLC aspect. Okay. Then when we talk about as such the smart manufacturing, we are talking about smart factories, and even as I was quoting earlier, the dark factories, for instance. Okay, so it involves a lot of decision making, and then how we complement the physical science and how we try to understand, interpret, and then develop a technology. So as such, that is a difficult aspect that we have to understand. Okay, so as such, if you try to understand the players who are involved, okay, so this is a very big process as such. Okay, so if we are talking about data, if we're talking about a knowledge, and if we are talking about something like the insights that we have to take on data, how we have to clean the data, because as such, when we are having data and we are taking decisions based on data, and if that is defining as a control aspect. One simple example here we can take. So the coordinates of placing a mirror on a automated vehicle. So if it is based on the coordinates, so let us say a automobile manufacturing unit is assembling a car, and then the mirrors have to be placed just in front of the first what I would say, like the window. So instead of placing the mirror at the first window, if it places the second window, just because the conveyor has moved, or whatever assembly conveyor has moved by 2 inches, so what happens? So it is like a flaw because of one small error. So this control aspect as such would be like controlling all in tandem, and then ensuring that we achieve the target. Okay, so the objects, equipment, processes, people, environment also all will play an important role when it comes to control engineering, and this is like a aggregated big data. So when we are talking about this as such, it would be like smart connected products, enterprises, external devices, disturbances, which have to be analyzed descriptively, diagnostically, predictively, prescriptively, and then we go with the manufacturing with the AI. So as such, this involves a lot of process in automation for control with AI. Okay, so the smart manufacturing as such is one aspect. So data-driven intelligence and how we control it, and then where we apply it. Because my talk is mostly on the control aspect. This control where we apply, we control with AI. Where do we apply? Is the control engineering in process industries is what we do. And then here, if we are trying to see like what are the key aspects of that. Okay, so if I'm talking about a robot or a SCADA system that is being controlled, how my deep learning models will help me. So at the basic level, if my device or my sensor or my actuating device is being used, and that has to give data which is stored in a machine, and then it has to be processed by a PLC or a SCADA, and then how I take a decision for a robot arm to move. So that is like controlling the arm. So how good is that? And what are the controllers? Like if you are using a simple controller like PID, or maybe a complex H infinity controller, or maybe any other controller. So how the decision is taken is something that involves a lot of research. Okay, so as such, when we are using this, the malfunction detection using something like neural network, for instance, is one aspect. So when will we define so what is the problem and how do we understand it? Okay, so these are some important things. And then if we try to extend it, so for instance, something like the neuro adaptive control. So this is like some work that I've done like 20 years back by when I was in US. So basically taking a nonlinear multi-layer network, and then we adapt to bring the fine tune the weights. Okay, so these are like fine tuning with AI would be more smarter these days. So for instance, this is a snapshot of some of the research that we have done at that time, where we are trying to stabilize a double inverted pendulum, which is like a test model or the base model for fine tuning what is called as a I mean, double inverted pendulum. You have, as a test bed used for fine tuning something like the missile vehicles and all. Okay, so how do I reduce the training error, and then this has to be optimized with the particular system or with my AI training. Okay, so when I'm talking about training error and how I can reduce the training error is something that we have to understand. Okay, so as such, another dimension is like the machine vision. But in the interest of time, because we just have like 20 minutes, and I just skip some things. But vision. Okay, so as the machine vision with the deep learning is one important aspect. Again, when it comes to the control aspect for fault diagnosis, and then when it comes to different industries like the aircraft engineering or chemical process or wind turbines and all. Okay, so simple examples where we go in is like robot object grasping and how we can adapt these control techniques, and then how we do it for the predictive analysis for defect diagnosis and all. And then uh, whatever data that we have, like how we can extract and how we can abstract. Also, the classification of data is very much important, and how we can do it in the best possible ways is one important thing that we have to understand. And then what are the processes that that are involved. Okay, so I'm not going much into the machine learning models for classification, like we have done in the past 2 days. Speakers have spoken about different learning algorithms. So you can use anything based on what is the data set that you're trying to handle, and what is the industry that you're dealing, and how we are trying to analyze it. Okay, so there would be like the steps as such to perform machine learning would be more or less same, irrespective of the the algorithm that you are using. So you basically collect data and do the feature engineering, and then train your first model, and then tweak it for the analysis. Okay, and then like the data collection and separation, or what we have to do for the data pre-processing and how we have to do it. Okay, so these are like traditionally how we have been doing data analytics is something that comes into picture here. And then that is something that will be used in our engineering. So I'll skip some parts here. And then one important aspect that I just wanted to touch upon, what basically is the domain where AI will be helpful. Okay, so the effect of disturbances in control. Okay, because identification of disturbances is something that is not easy for a control engineer. As such, in control engineering, you might develop a robust controller or maybe a adaptive controller, but you might not be able to identify the disturbances that might pop in. So these kind of disturbances that might come up might have to be analyzed with AI. Okay, so the mitigation of disturbances and how to identify the disturbances. So the solution to this is your expert system. That is like the goal of control engineering, where you have an expert system which will do the control part with AI without troubling the user. Okay, so that is like the effect of disturbances, and the solution will be yielding a expert system. Okay, now when it comes to the expert systems, as such, is a knowledge-based system, and it basically employs application domain used on interfacing. So basically needs and what is the human competence, because when it comes to industrial control processes and all, historical data is very much important, and then based on the historical data, these expert systems can come up with a solution to solve the real problem, which require as such a specialist human expert, which can I mean, like the decision, like emergency, if there's a machine failure, what has to be done instead of the human being taking the decision. Maybe an expert system can take the decision. Okay, so what is it that we achieve with it? We achieve something like enhanced productivity, augmented work process, and man hours can be as such saved. So basically, most of these technology developments that we are doing, as such, will help us in reducing the man hours, and then fine-tuning our mechanism such that we have some time to ourselves. So there are, as such, these days many companies which are using different expert systems, or they have like in China we have the freight train systems, and then there are electricity market forecasters, there are rule based engine for mobile games. So different aspects. Okay, so the conventional systems and expert systems, there is always a comparison, and then how we actually build these systems and how we can use it is one aspect. Okay, so like the conventional system mostly are algorithmic, and then expert systems as such will be heuristic, and then they represent the usage of knowledge, and then how we actually represent the data is what was conventional system. Like you are taking a classical control mechanism, you are actually plotting some data, and then you are trying to analyze what was the energy used, or you are doing calculations. Okay, so all this can be exported as such, exported to AI now, so that the expert system will do it. It will deal with the qualitative analysis, and then it will improve the effectiveness of the code. Okay, so that is what can be achieved. So as such, the huge amounts of data that are there in industries, for instance, the 24/7 operating industries as such will have huge amounts of data, which can be used for training the expert systems and making sure that human intervention is as such reduced. Okay, so these are like some slides where I was just saying about different features, like how human expertise will define and expert systems are doing. Now, conventional systems had humans interpreting the classical controller uh, and analyzing it. Okay, the expert system with AI would as such define and understand that particular data, and will be able to guide us for achieving the required target. Okay, it is like even when you're talking about sales or any control aspect of a particular, because in any industry you would have n number of control parameters. It is not like only the machine control is there. Okay, so it is about controlling many aspects, and these expert systems will as such help us. Okay, so once we talk about this structure of expert system. Okay, so again, this the control engineering, where we are being driven, we are having a user, and we are having a user interface. We have an inference engine, which have a knowledge base, and then there will be a knowledge engineer, or maybe as such a traditional engineer who would acquire knowledge from different sources. You would take advice from human systems, and then we would develop an environment or a control strategy. So the development of the control strategy as such is what we are trying to do it with less human hours here. Okay, so that is what we are doing when we are using AI. Okay, so the conceptual architectures and how how they get modified is some important aspect. Again, this is a important on what are the players, or who are the players in the control structures, defining the control structures if you are talking about a complex system. Okay, so the architecture, what is the input, what is the output, and what is the knowledge base, how we are using it, and how we are controlling. Okay, so one of the last things that I wanted to talk uh, was expert system with AI for system regulation. Okay, so when I say that, so the system regulation as such uh, is about the ability of a control system to respond to inputs and disturbances within a fixed limited time, and ensuring the stability. Okay, so it is like an anti-lock braking system. Okay, now you all know that these days the vehicles are very powerful. They have the anti-lock braking systems, and the drivers are well equipped when to apply brake, and then how to use it. But where these expert system can help us is like it will tell us when to change the brake. Okay, so the usage patterns of the brake by the drivers can be analyzed by the AI, and then that can use as a data set for developing our anti-lock braking systems, and then ensuring that we regulate the wheel speed, and then ensuring when to change the brake. Okay, so this is like one aspect. So which I thought might be helpful, because that is a future research problem where people study the brake usage patterns and with AI, and then the AI captures the usage patterns of the brakes, and then develop a mechanism to indicate or give us a suggestion. Okay, the brake might not be able to control the vehicle at that particular instance, and then you might be able to tell that the AI will tell, okay, So they in the next 15 days, you have to change the brake based on your usage pattern. So that is like the target of control engineering. So if I'm taking about a vehicle being used by a human, and the human knows how to use the brake, but he doesn't know the wear and tear of the brake. So the AI will assist and help us understand when to change the brake. So that is what is one example of what we are trying to do with an expert system with AI developed for control engineering or applied to the automobile or any control aspect. Okay, so in the conclusion part, what I basically want to tell, control engineering have some advantages like the problem identification could be speeded up with AI because abstraction can be done with AI properly, because when you are defining the keywords, the AI is able to tell, okay, these are the existing problems and this is how different companies are able to solve it. So engineering solutions as such can be developed. We can improve the accuracy and precision, as I'm talking about some of the examples like the PID controller tuning and all. And then we can also develop expert solutions which will mitigate the disturbances with AI. So these are some aspects. These are some of my references that I have, like some research papers that I have studied and over the period of time.